S to transformation SOT inverse, that is equal to inverse of T, composition of inverse of the transformation T inverse and S inverse, right. So all these three questions we one by one want to check, and for that definitely we use the standard matrix for the linear transformation. T and S both are linear transformation, so easily we can find the standard matrix, right, as we already write down before the previous example. So and this is a 2 cross 2 matrix, right, because our transformation, both the transformation are linear and from R2 to R2, so the domain and codomain both are R2, so definitely whatever our standard matrix is in size of 2 cross 2. Okay, so let's see how we use the standard matrix, and using that standard matrix how we prove all these sub questions, right. Let's see. The Txy is equal to x plus y x minus y, and Sxy is equal to 2x plus y x minus 2y. So the here the standard matrix T, that is 1 1 1 minus 1, and standard matrix S, how is coming from the first row 1 1, that is coming from the first coordinate x plus y. In x plus y the coefficient of x and y, that is 1 1, and x minus y the coefficient of x y, that is 1 minus 1, right. And here is the standard matrix as the coefficient of S, that is 2 1, and the coefficient of the x and y in the second coordinates, that is 1 minus 2. Okay, so here determinant of T, that is equal to, first of all we want to find determinant of T, that is 1 into minus 1, that is minus 1, minus 1 into 1, that is minus 1, minus 1 minus 1, that is equal to minus 2, not equal to 0, and determinant of S, that is equal to minus 4 minus 1, that is equal to minus 5. Okay, so if determinant is non-zero for the standard matrix, we can directly say that the transformation is 1 1 and on 2. Okay, transformation is 1 1 and on 2. Here the same process happen here. Now also we know that the standard matrix of T inverse, that is same as the inverse of the standard matrix T, and similarly the standard matrix of S inverse, that is same as the standard matrix of inverse of S. Okay, so this important property we will use to find the T inverse. First of all we want to find the inverse of the standard matrix T. In 2 cross 2 matrix we can directly write down the inverse of the standard matrix, adjoint of T upon determinant of T. Determinant of T that we already know, minus 2, right. Now what is adjoint of T? In 2 cross 2 matrix, if you want to find the adjoint of T, that is just we have to interchange the main diagonal entries, that is minus 1 1. Okay, just we have to interchange the main diagonal entries, that is minus 1 1, minus 1 1, and then we have to change the sign of the another diagonal entries, that is minus 1 1. Okay, so and upon determinant, so minus 2, and inverse of, so that's why inverse of the standard matrix T, that is minus 2 1, minus 2 minus 1, minus 2 minus 1, minus 1 2 divided by minus 5. Okay, now next is T inverse. So that is standard matrix of T inverse, that is 1 by 2 1 by 2, coming from this, see 1 by 2 minus 1 by minus 2, so 1 by 2 minus 1 by minus 2, that is 1 by 2 1 by 2, and this is not a standard matrix of T, but this is the standard matrix of inverse of S, right? Just correction here, that is, this is not T, this is S. So the standard matrix of S inverse, that is 2 by 5, 1 by 5, 1 by 5 minus 2 by 5. And now we have the standard matrix of T inverse as S inverse. So we can write down the T inverse xy and S inverse xy using this standard matrix. So T inverse xy, we can write, the first row is 1 by 2, 1 by 2. So we can write x plus y by 2, that is our first coordinate. And the second row is 1 by 2 minus 1 by 2. So that's why we can write x minus y by 2. Now S inverse xy, that is equal to 2x, that is coming from the first row, 2 by 5, 1 by 5. So we can write 2 by 5x plus 1 by 5 y. So that is 2x plus y by 5. The second row is 1 by 5 minus 2 by 5. So we can write 1 by 5 into x minus 2 by 5 into y. So that is x minus 2y by 5. Okay. Now, so this is our T inverse xy, this is our S inverse xy. Now SOT, S of x plus y, x minus y, right? We want to find the composition of SOT first of all. So how we define T of xy? Just, this is our T of xy, x plus y, x minus y. So when we find the composition of S with T, SOT, that is S of T of xy, that is x plus y, x minus y. So S of x plus y, x minus y. Now these two coordinates are operate on the definition of S. What is our S of xy? S of xy, that is 2x plus y, x minus 2y. So 2 into, so basically we have to understand that 2 into the first coordinate plus the second coordinate, and then x first coordinate minus 2 into the second coordinate. So first of all 2 into first coordinate plus second coordinate. So this is 2 into first coordinate, that is x plus y, plus second coordinate, that is x minus y, and then first coordinate minus 2 into second coordinate. You can see x minus 2y, that is first coordinate minus 2 into the second coordinate. So we can write x plus y minus 2 into the x minus y, that is equal to, when we simplify we get 3x plus y and then minus x plus 3y. Okay. So if you want to write down the standard matrix of SOT, that is from this equation 3x plus y. So the first row is 3 1 and the second row is minus x plus 3y, minus x plus 3y, that is minus 1 3. Okay. Now again, if you want to find the inverse of this composition of S with T, that is equal to inverse of the SOT, that is equal to, that is exactly the standard matrix of SOT inverse. Okay. So if you want to find the inverse of this 2 cross 2 matrix, again we have to find a adjoint of that matrix upon determinant of that matrix. Determinant is quite easy because determinant of this 2 cross 2 matrix is 3 into 3 9 minus 1 into minus 1, that is plus 1. So 9 plus 1 10, correct. And if you want to write down the adjoint of this matrix, that is we have to interchange the main diagonal entries 3 3 and then change the sign of the another diagonal entries, that is minus 1 become 1 and 1 become minus 1. So minus 1 1 here, right. So that is equal to inverse of the standard matrix of SOT, that is 3 by 10 minus 1 by 10 1 by 10 3 by 10. Okay. Now next SOT inverse, we can write 3x minus y by 10. Okay. That is coming from this standard matrix 3x minus y by 10 and then x plus 3y by 10. Okay. Now T inverse, we already know that the standard matrix for T inverse, that is 1 by 2 1 by 2 1 by 2 minus 1 by 2, and standard matrix for S inverse, that is 2 by 5 1 by 5 1 by 5 minus 2 by 5. We already find this two matrix. You can see this is the standard matrix for T inverse and for S inverse, correct. So so just I repeat this two matrix here and check that the T inverse multiplication of T inverse with S inverse, what will we get? 1 by 2 1 by 2 1 by 2 minus 1 by 2, then 2 by 5 1 by 5 1 by 5 minus 2 by 5, that is equal to 2 into 1 plus 1 by 10, so 3 by 10, and then 1 by 2 into 2 by 5, that is 2 by 10 minus 1 by 10, that is 1 by 10, and then 1 by 2 into 1 by 5, that is 1 by 10, 10 minus 1 by 2 into minus 2 by 5, so plus 2 by 10, so 3 by 10. So correctly you can see this is exactly the standard matrix of inverse of SOT. So from these two equations, this equations and this equation, we can write that inverse of SOT, that is same as T inverse, composition of T inverse with S inverse. Okay, so here we check all this sub question of this question. You can see this is our main question. We already proved that S and T are 1 1 using the finding the standard matrix of S and T, and prove that the determinant of that two standard matrix are non-zero. So S and T are 1 1. Also we find formula for T inverse and S inverse and inverse of SOT, and then also we finally verify that inverse of SOT, that is same as T inverse, composition with S inverse. Okay, so all these questions we already prove in this solution of this question. So here to complete the solution of this question. Next question, question 5. Question 4 is complete now. Next is question 5. Find a matrix P that diagonalizes A and determine P inverse AP. Now what is A? That is 3 cross 3 matrix, minus 1 4 minus 2 minus 3 4 0 minus 3 1 3. Okay, so first of all we have to find the eigenvector, eigenvalue, and then corresponding to eigenvalue we have to find all the eigenvectors. Corresponding to that eigenvector we can find the matrix P, and then using that matrix P we can find P inverse and then multiply P inverse AP. Okay, so this is our process to solve this example. It's quite important example. This type of example always ask in this paper. Okay, vector calculus, in this vector calculus and linear algebra paper. So just try to understand properly. The non-singular matrix P containing eigenvectors of A as column diagonalizes A. The characteristic equation. So first of all we have to find the eigenvector, and to find eigenvector we have to use the characteristic equation and solve this characteristic equation, right, in quadratic form, and we can find lambda 1, we can find eigenvalues. So the non-singular, this is our characteristic equation. Determinant of A minus lambda I, that is equal to 0, that is minus 1 minus lambda. Okay, minus 1 minus lambda. Just simply only the in main principal diagonal elements we have to add minus lambda. So we get minus 1 minus lambda, then 4 minus lambda, and then 3 minus lambda in main principal diagonal element. Okay, then 4 minus 2 minus 3 0 minus 3 1, all other elements are same, just changes are becoming only in the main principal diagonal elements. We have to just minus lambda add in all these elements. To solve these determinants it's quite easy. You all know that how to solve the determinant, that's quite easy. This is just a 3 cross 3 determinant. So here is the some simplification, that minus 1 minus lambda, 4 minus lambda. So just see and try to understand. Okay, I think I don't need to explain in this step, because this is just a simplification of determinant. Okay, how to solve 3 cross 3 determinant, that you should know. Okay, so finally we get these equations, that is lambda 1 lambda 2 lambda minus 1 lambda minus 2 lambda minus 3, that is equal to 0. The eigenvalues of A are 1 2 3. Okay, now the eigenvectors of, now we want to find eigenvector corresponding to eigenvalue 1 2 3. Okay, so one by one we find first of all eigenvector corresponding to 1, then 2, and then 3. Okay, so the eigenvector of x corresponding to the eigenvalue lambda is given by the matrix equation A minus lambda I into x, that is equal to 0, that is minus 1 minus lambda. So 4 minus lambda, 3 minus lambda, 4 minus 2, minus 3 0, minus 3 1. Okay, again we have to convert, we want to find the eigen vector corresponding to lambda is equal to 1. So put lambda is equal to 1 in this equation, we get minus 2 4 minus 2, minus 3 3 0, minus 3 1 2. Now we have to use augmented matrix. So here is the augmented matrix, and now we want to convert just the same matrix, right? Here written minus 2 4 minus 2, minus 3 3 0, and minus 3 1 2. You can see the same matrix I written here, minus 2 4 minus 2, minus 3 3 0, and minus 3 1 2 oblique 0 0 0. So this is augmented matrix. To solve these equations, we have to convert this matrix into a row echelon form. So here is the next process. We multiply first row with minus 3 by 2 and add into the second row, and we multiply the first row with minus 3 by 2 and add into the third row. So that's why these two elements become 0. The first row is as it is, minus 2 4 minus 2. The second row is 0 minus 3 3. The fourth row is the third row is 0 minus 3 3. Okay. Next process is we have to multiply second row with minus 5 by 3 and add into the third row. So the first and second row are as it is, minus 2 4 minus 2, 0 minus 3 3. The third row becomes 0 0 0. Now using this, now this matrix in row echelon form, and now we can solve the equations. We get two equations, minus 2x1 plus 4x2, minus 2x3 is equal to 0, and then minus 3x2 plus 3x3 is equal to 0. So here is our two equations. Take x3 is equal to t. Okay, because the third column we don't have leading entry, so that's why we take x3 is equal to t, and x2 is, so that's why x2 is equal to t, and put these two values, the values of x2 and x3, we get x1 is equal to t, right? Hence the eigenvector corresponding to lambda is equal to 1 is 1 1 1. Now similarly we can find the eigenvector corresponding to lambda is equal to t, right? Similar manner, just similar method, we can find the eigenvector corresponding to lambda is equal to t 2, and that is 2 3 3, and corresponding to lambda is equal to 3, we can also find the eigenvector, that is 1 3 4, right? So all these three eigenvector we have to write down as a column, that is exactly our matrix P. So you can see this is 1 1 1, the first